bucket with sand, or what's the?
Yeah, I'm gonna do a giant bucket. I'm gonna bring in a thing of sand, and then it's just gonna progressively get loaded.
Okay.
I think the fun part about this is the fact that I kind of changed it up from how the American Society of Civil Engineers does it, where they specify where the load is. Yeah. This is the one part that I think is going to be probably a little bit more challenging. You have to design it for any possible location.
Oh, any location?
On the road deck. Yeah. So imagine as if it's a moving load. Generally, for like bridge design or in other structures where you may have like an anticipated moving load, you need to design for the load to be at any particular point. So we'll actually get into a little bit of it once we start getting into shear and moment diagrams, which is in chapter 5. So it does become a bit fun once you start getting into the weeds of how to analyze that. But we basically develop what's called shear and moment envelopes, which is basically the worst case loading at any given point. Does anyone have any questions so far about the project? Yes.
So if it could be anywhere on the bridge, that loading, should we not account for the loading plate hole that's on the drawings? I thought I saw that. Yeah.
I updated the figure. Basically, I guess the best way to kind of work about that is to have two sides of a road deck with a slit in the middle, and then the load can be placed anywhere.
A slit in the middle?
Yeah, because the way that I'm planning on getting this to work is it's going to have a little mechanism like this with a bearing plate right here that's going to basically bear onto the road deck. So you kind of want to strategically place also your stringers on to be able to handle the load, because the road deck itself, unless you make that the primary load bearing element, it's not going to likely be able to handle the load unless you make it very thick. Yes?
Do we get the dimensions?
Well, this is not what we're going to be using.
Okay.
I actually asked if Andres could make it. So once he comes up with an idea on what dimensions are likely going to be needed for it, we can kind of work from there. But right now, you should be able to do a preliminary design assessment, just assuming 70-pound point loads, because then that would probably be the most conservative load casing that you can imagine is point loads, because then it's basically like an infinitesimally small area, so the force is going to be very concentrated versus distributed over a certain region. Any other questions? Yeah?
For the RFP, you want that typed up?
Yeah, just a simple like 1-2 page written document. Again, just explain to me problem statement, what
This week or next week?
this Wednesday.
This one's-
Yeah. Just because I really want to get an idea on who's going to be in what groups. Since the majority of students voted yes, everyone has to work on the project. All right. So I'm assuming everyone is okay with working on the project. Again, you can work in groups because I don't want you guys being too stressed out, because I know a lot of you are taking a bunch of other classes too. So the last thing I want is you guys stressing out about the entire project. All right. I guess let's get into it. So last class, we started our conversation on pure bending and the design thereof for pure bending, where we talked about the stress distributions within flexural members, and we discussed these new terms, S for the elastic section modulus. Is my screen frozen? Interesting. I do not think my screen. Let me read that. I hope it's working. Okay. I don't think this is working still. What is this going on? I'm gonna need to go get that person again because this is not working now. Is it just slow? I'll be right back. I'm gonna go see if I can actually get that real quick. Let's see if this works. That should be that. Throw this into here. And then source search. Let's see if this works. Awesome. Thank you.
You're welcome.
All right. I will make sure not to forget my.
Leave that on the desk in the office.
Yeah, sure thing. Thank you. All right, so last class we basically talked about the stress distribution within flexural members, how it's generally maximum at the furthest distances from the neutral axes. And the neutral axes are where the flexural stresses, the normal stresses due to bending, are 0. So today what we are basically going to be continuing is a discussion about the about different considerations for flexural members explicitly. This includes, I think, what chapter did we leave off on? Was it 4.3 or 4.4? Do you guys remember? I just want to make sure that we're at the right point. I don't know if you guys even wrote it. Did you guys see the deformation in the cross-sectional plane for elastic curvature?
I
No?
don't think so.
Okay, so we'll
The
just,
last thing we did was the centroid practice problem.
the centroid stuff?
Yeah.
Okay, so then here we'll just continue talking about the deformation and the cross-section plane. Basically, this is just going to be kind of a summary of everything that we've talked about so far, where you should recall that your curvature equation should be equal to whatever the internal moment is, divided by the elastic modulus, multiplied by the second moment area of inertia. From here, the strain, which in this case is going to be the normal strain or the strain in the x direction, is going to equal the negative curvature times its y position, because again, the strain in the x direction varies with respect to its horizontal location. So the strain at the neutral axis is obviously going to be 0 because it's not deforming, but the strain at the upper and lower fibers, the top and bottom fibers, the extreme fibers, is going to be maximum. And then we can calculate the normal stress using the elastic modulus multiplied by the strain in the x direction. Now, what does this mean for sigma y and sigma z? Well, because of the Poisson's ratio, remember lateral stress and lateral strain, the lateral stresses are of course going to be 0 because for flexural members in a lot of instances the beam is unrestrained to lateral deformation, but epsilon y and epsilon z are non-zero. All right, Now, if you guys remember, for lateral strain, what does lateral strain equal to? Think back to our previous lectures. I'll just subgrade it to epsilon L, which is just equal to epsilon Y. What did we say the lateral strain was equal to? How did we relate that to normal strain? Exactly. It's negative, whoops, my pen turned off, negative Poisson's ratio times the normal strain. In this case, epsilon y and epsilon z is equal to negative Poisson's ratio times epsilon x. All right, so we plug in for epsilon x, and we get negative Poisson's ratio times negative k times y, which just gives us Poisson's ratio times the curvature times y. Let me copy this, paste it onto another slide, and then I'm just going to erase all of this really quickly. All right, so from here, we can calculate anticlastic curvature just by expanding on this function. So we know that k, again, is equal to 1 over rho, which is the radius of curvature. So we can then rewrite this to say that epsilon L is just equal to Poisson's ratio times y divided by rho. We can then just kind of clarify this term, so we can define a new term, which we call Poisson's ratio divided by rho. We set this equal to a new term called 1 over rho prime, which is basically the radius of anticlastic curvature, which then gets defined as k prime. And so anticlastic curvature just becomes equal to that k prime times rho. And then from there, we can calculate the deformations accordingly. So these are basically the lateral deformations that would be experienced within this cross-section, laterally speaking. Any questions about this? This doesn't exactly become too significant in certain aspects of design, but it is kind of important to understand that, you know, even though we're dealing with flexural members, they can still deform laterally. And they're, of course, a function of the curvature of the beam. All right. Now, the next topic is a personal favorite of mine, is members made of 2 or more materials. Composite materials, we call these. You guys remember composites for axially loaded members. Now it becomes much more of a complicated situation dealing with composites in 2 or more materials. So, what's one of the things that we need to recall about composite materials? What's something that we know? Yes?
Their elastic modulus is going to be different, so they're like how much they deform under a certain load is going to be different for like each.
Yes and no. Yeah, try.
The strain is the same?
Yes, but in this case, because we're dealing with bending, the strain as a function of y is not exactly the same. But we know that the strains, even though they can vary in the y cross-section, we still need to apply some variation of compatibility. So, for this case, everything is the same up to the point when we introduced material behavior, or Hooke's law, where the deformation we set equal to the normal strain, which is going to be the strain in the x direction, multiplied by negative curvature times its y position. K we don't exactly know, so K is sort of an unknown at this point. We need to be able to determine that. And then what else do we know? What are the two equations that we needed to determine internal forces of composite members? We had compatibility, which is going to be our deformation. What's the other one? Equilibrium. And here, we're going to have technically two equilibrium equations. Let me just replace these with like just dots. Our first equilibrium, if we think about it, is going to be forces in the x direction, right? Because we're going to have stresses top and bottom. The forces have to be able to cancel out. So we know that the sum of the forces in the x direction has to equal 0. But obviously, what are the components of all of the forces? Simply put, it's just going to be the integral over the area of the stress in the x direction times the area. What else? Well, since we're dealing with bending now, we also have a moment term. This moment term is going to be sum of the moments about the z direction, which is equal to, again, 0, which has to equal the sum of the stresses, negative y, times sigma x, times dA. But the moment is technically applied, so we need to add whatever that bending moment is, which is just going to be negative m in this case, which then we can just rewrite to say that the bending moment has to equal negative y sigma x dA. Another way, which is probably a better diagram to kind of show all of this, is a diagram that basically looks like this, right? Where we may take the moments about the neutral axis and do some of the forces about that x direction. So let's just do that really quickly. From some of the forces in the x direction, we know that this has to equal 0, which we just take as the integral of sigma x times dA. Now, how many areas are there? There's two areas specifically, two areas where stress is going to develop. All right, so we split this up to just be the integral of A1 of sigma x dA plus the integral of area 2 sigma x dA. Area 1 and area 2. What is stress equal to? Well, if you guys recall, stress is just going to equal the elastic modulus times strain, which another way we can write strain is from the curvature equation multiplied by the y-coordinate. So what we get now is 0 is equal to the antiderivative of A1. E1 is going to be the elastic modulus of material 1. The curvature is going to be our compatibility. So we know that curvature has to remain the same times the y-coordinate, dA. And then if you think about it, we are just going to have the same exact equation for material 2, E2 ky dA. I forgot a negative sign here, so make sure that gets incorporated. That's why we have the negatives here and the subtractions. All right. Now, there's one problem with this, and it's two unknowns, right? We still have too many issues to have to deal with. So one of the ways that we really solve this is through a transformation. When we were dealing with composites previously, we were kind of indirectly dealing with it through a ratio of the elastic moduli. Here for bending members, we need to define kind of a new term where we basically define an equivalent cross-sectional area to provide an equivalent amount of stiffness. It's a little weird. For axial members, it's less prevalent, but you guys did deal with this. So what we do is we define this new term. We call it N, which is basically just the modular ratio, we call it, which is just equal to the ratios of the given materials, E2 over E1. And what this does is it basically allows us to find an equivalent stiffness for 2 to relate back to material 1. So, knowing this term now, we can rewrite everything for equilibrium. So, 0 is just equal to the integral of area 1 times negative E1 ky dA plus A2 times, now it's going to be E1 times N, since E2 is basically just equal to N times E1 times Ky all multiplied by dA. And again, those are negatives, so I'm just going to take those negatives out and just throw them right here. Yeah.
Can you just go back to the last slide for a second?
Sure thing. Any questions about this so far? All right, that's basically just equilibrium in the x direction is just those integrals, all right? We know that they have to equal each other. Now, what we kind of still need to know is that term k, because we don't exactly know what it is. So let's just do sum of the moments. Now, if we were looking at this, where might be a good location to do sum of the moments to determine equilibrium?
Would be the neutral axis.
I would prefer the neutral axis, because then everything is just with respect to a point of known value. So we could do the sum of the moments about the neutral axis. This is, of course, the moments about the z coordinates. So obviously, we're looking at sort of this stress distribution here. And we know that this has to equal whatever the applied bending moment is within the material, which then we expand outwards to just say negative y sigma x times dA. We expand these equations further to express them in terms of the curvature of the beam, which gives us the integral about area 1 times E1 ky squared dA plus the integral of area 2 times E2 ky squared dA. Again, E2 is just equal to N times E1. So we can rewrite all of this just to be equal to E1 times K, all multiplied by the integral of a1 y squared dA plus the integral of a2 y squared dA. N and y squared dA. Anyone know what the thing in the parentheses is? What does it look like? I'll give you a hint, it's from statics. It's just the second term is a little bit confusing. Yeah,
Is that moment of inertia?
exactly. It's the second moment area of inertia. So the first term, that integral of a1 y squared dA, is the first moment area of inertia of that first term. Now the second term is the second moment area of inertia of area 2, but we need to transform it to get the entire cross section all as one material. So what we end up with is just E1 times K times what I'm going to call I transformed, which is basically just the second moment area of inertia of this shape right here. All right, so don't be using just BH cubed over 12 and looking at just this cross section, because that would be an improper way to look at it, because then you're not accounting for the variation in stiffness. What you need to do is consider that transformed cross section, which is a theoretical cross section that we use to account for the ratio of the stiffnesses between the two materials. And that's basically how you would, that's basically just an introduction of what the transformation process would look like. So just as kind of, whoops, let me not delete that. So just as kind of a summary, let's just really quickly just erase all of this. All right, so what we want to do is for transformations, material 2 using n is equal to E2 over E1. So that's 2 to 1. And then from here, calculate I transformed. Which hopefully you guys should know how to do that from statics. The only difference is just kind of drawing out that new shape and then solving for the new shape. And then lastly, just applying Hooke's laws to get the stress, which you can calculate the stresses using sigma x is just equal to my over I, or nmy over I, which is just going to be the transformed second moment area of inertia. Let me actually just rewrite this slightly. So if we wanted the stress in material 1, it would just be my over I. But if we wanted the stress in material 2, you would need to multiply it by n to get that. Does that make sense? And what this will do is obviously by multiplying it by that term n, it'll actually increase the amount of stress, because if you think about it, a larger, stiffer material will generally want to take on more load in order to compensate for the deformation. Make sense? It's like trying to bend a piece of steel with Play-Doh on it. Like, I mean, the Play-Doh is not going to take any load whatsoever, but it'll deform at the same as the steel. So let's just do a really quick example of just transforming the cross-section. So in both instances, we should get the same answer for what the strains would be, but there are two different methodologies. So for the option 1, if we were to do the second moment area of inertia calculations for this cross-section, we should get 1 over 12 times b times 3a cubed, whoops, that is atrocious, plus 1 over 12 times b a cubed, which is just going to equal 7 over 3 ba cubed. And that's going to be the second moment area of inertia for I1. Now, if we did it for option 2, we should get a smaller answer. So 1 over 12 times b over 2 times 3a cubed plus 1 over 12 times b over 2 times a cubed. Basically, what we're doing is it's just solving it just like this. This is all one block. This is all another block. Similar here. This is all just one block right here. And then this is that other block. You guys can use the tables if you want to just to validate this. I'm just kind of speeding through this because hopefully you guys should know how to do this, but you could solve it however you want. You should get the same answers regardless. And so those are the second moment areas of inertia that we end up getting. Oh, let me give you guys the final answer for this. This should just contract to 7 over 6 ba cubed. All right. Now you guys might notice there's 2 second moment areas of inertia. Why is that? It's because each one represents a different material. Option 2 is going to be twice the elastic modulus of option 1. That's given from this 2E term right here. So we know that the gray highlighted is about twice as stiff as option 1. All right? So we account for all of this now by just plugging it into the curvature equation, which we know is just equal to m over EI. So when we plug in everything, we should get 3m over 7 EB a cubed. Now for option 2, I'll call K2 and then this K1. If we plug in everything using this equation m over EI again, this is going to be E1, E2, I1, and then I2. We get 6m over E2 is equal to 2E times 7b a cubed, which guess what? K2 is just going to simplify to 3m over 7EB a cubed. So the curvature is the same. And then, of course, if we wanted to calculate the strains, you would just multiply this K term by whatever Y value you were interested in. And then, of course, the stresses you can calculate from there. That's just from the basic Hooke's law equation. Sigma is equal to K E epsilon. Now that's how to deal with composites that are of 2 materials that both behave linear elastically. But there is a particular material that especially those going into civil engineering will deal with, and that is reinforced concrete. Reinforced concrete is kind of its own separate beast in itself because of the complexity of the material, but we can perform elastic analyses using some general assumptions about the material. So in this case, we assume that because the concrete, we all know concrete is weak in tension, right? We assume that all of the tension carried by the concrete is all of the tension carried by the cross-section is carried by the steel and not at all by the concrete, and only the concrete carries the compression. So, what are our general steps? Again, we want to transform the steel cross-section. So we use the modular ratio to relate the elastic moduli of the steel to the elastic moduli of the concrete. From here, we need to determine the neutral axes. How do we do that? Well, we need to use the first moment areas of inertia, which is just that Q term, which if you guys do the table, should be the A times Y divided by Y. So to find the neutral axis, we need to calculate Q, which is equal to y bar, which is just equal to the sum of the area y bars over the sum of the areas. Simply put, for concrete, once you guys do all of the calculations, should just simplify to B times X, where B is the width of the concrete beam, times X divided by 2, which Bx is the area of the concrete compression block, and X over 2 is the centroid of that compression block, minus the modular ratio times the area of the steel, multiplied by its perpendicular distance, which is D minus X. So this is basically just the transformed section of steel, all to an equivalent stiffness of concrete. All right, and from here we would find where X is. And that's the neutral axis from the top. Let me paste this. From here, after we determine the neutral axis, next step should just be find the transformed cross-sectional area. Second moment area of inertia, which this, when you do the tables, would just simplify to 1 over 12 bx cubed plus bx times x over 2 squared plus nas times d minus x squared. So the 1 over 12 bx cubed is just your ix from like your standard rectangular tables. And then you have the sum of a dy squared. That's what those other two terms are. One thing you'll note is we're not accounting for the circular component of the polar moment of inertia equation, and that's because the size of the rebar is generally so small that we just ignore it completely. So we basically just approximate it to 0. And then lastly, from here, we can calculate the stress in the concrete using my over that I transformed. I'm just going to write T just to simplify it. I don't really feel like writing the whole thing. And then we can calculate the stress in the steel using Nm times d minus x, because that's its y coordinate, divided by IT. And so if we wanted to find the maximum stress in the concrete, the Y term here just basically becomes X, because that's the highest value that we can use. All right. I think a nice example should hopefully do us good. So a concrete floor slab is reinforced with 5/8 inch diameter steel rods placed 1.5 inches above the lower face of the slab and spaced 6 inches on center. So these are number 5 bars. The modulus of elasticity of the steel is set to 29,000 KSI and 3,600 for PSI. There's an applied bending moment within the slab of around 40 kip inches for a 1 foot width of slab. So we're basically analyzing the slab on a per foot basis. It's actually a very common thing instead of analyzing it for like 50 feet in length, just assuming a 1 foot section. All right, so what we want to do is basically perform the elastic analysis to determine the stresses in the concrete and the steel. So what we need to do is we need to transform the area of the steel to an equivalent area of the concrete, which we should compute knowing that the modular ratio is just going to be the elastic modulus of the steel, which is 29,000 KSI, divided by 3,600 KSI for the concrete. We should get roughly 8.06. This is a unitless value, so don't write units for the modular ratio. From here, we would calculate the area of the steel as a transformed concrete region, which is just going to equal 8.06 times, if you think about the area of the bars, how many bars are going to fit in a 1 foot region if their bars are spaced at 6 inches on center? How much on average? Roughly 2 bars, right? If they're spaced 6 inches on center, you're going to have roughly about 2 bars in a given 1 foot cross section. So times 2 bars times pi over 4 times 5/8 inches squared, which this is going to give you that 4.95 inches squared that you see. Any questions about the bars at all? I just want to make sure everyone follows. I know not everyone's a civil engineer, so just want to make sure. All right. Now, we want to determine next the where the neutral axis is basically located. The best way we can do that, let's develop a table. So that way you guys just aren't using the equation straight up. Plus also, like, once you start getting into more complicated cross sections, not that I expect you guys to be working with that too much. It becomes helpful once you start working with the tables. So let's have a component, an area, inches squared, and then a y bar term in inches with an a y bar term in inches cubed, which this is that q term that we previously saw. So we're going to have the concrete and we're going to have the steel, but the steel should be transformed. All right? Now, the area of the concrete is just going to be 12 times x, where x is the location of the neutral axis from the top of the concrete beam. For the steel, on the other hand, it's just going to equal 4.95 because that's what we calculated. That's the transformed area of steel. From here, we calculate the y bar for each of the terms. So the y bar for the concrete is just simply going to be x divided by 2. And then for the steel, it's just going to be 4 minus x, where this y bar is basically, hold on, is it that? No, I don't think so. I want to do it from the top here. So the neutral axis for this is just going to be x plus 4 minus x, where this is our reference point. So we're finding the neutral axis with respect to that point. This actually just simplifies to 4 inches. All right, from here, we can calculate everything. Let me just pull up the calculator real quick. So this becomes 6x squared, and then 4.95 times 4 is just 19.8. What we get is 12x plus 4.95 is equal to 6x squared plus 19.8. And now to determine y bar, which is the location of the neutral axis, which is just going to conveniently be x. We set this equal to 6x squared plus 19.8 divided by 12x plus 4.95. And then this becomes a little bit of a nightmare to solve. So if you guys want to use the equations, you can. Let me just calculate it really quickly for you guys. Divided by 12 alpha x, whoops, that's 1.2. Whoops. I messed it up. Second, clear. Six x squared plus 19.8 by 12 alpha x plus 4.95. Calculate it. And 4x, we should get the neutral axis is equal to roughly 1.45 inches. So that's how deep that concrete compression block is. Any questions about this so far? This is basically like solving a quadratic equation. If you were to rearrange all of the terms, you could figure out the quadratic equation and then just figure it out from there. But yeah, I'm just too lazy to show you guys that. Copy, paste. All right. Let me erase all of this. With the neutral axis now computed, we can now compute the transformed second moment area of inertia. Now, keep in mind, what material is it that we're dealing with right now? Is it steel or concrete that we've transformed everything into? We've transformed everything to concrete. So everything is just going to equal our value for concrete. So what we need is a component tab, our area tab, which is going to be in inches squared, a dy, an ix term, inches to the fourth, and then an ady squared, inches to the fourth. All right. So for the concrete and for the steel transformed, the area of the concrete is just going to be 12 times whatever value of x we just previously computed. You should get 17.40, give or take. For the steel, it wasn't a function of x, so it's just 4.95. For dy is just another way of saying whatever your y bar was of the previous components multiplied by y bar. In this case, it's just going to be whatever this value is minus x. So in this case, it's going to be 1.45 alpha x over 2 minus alpha x. This is going to be about 0.73, I believe. And then this here is going to be 4 minus alpha x, which is about 2.55. For the steel, because it's a very small diameter bar, this just approximates to 0. The reason being is because Ix for a circle, I think, is like d to the 4th or pi d to the 4th divided by 64, which if d is 0.625, you're going to get some value in terms of like 0.00 something. So it's very small. So it makes no contribution to the calculations whatsoever. But for the rectangular block, it's just going to be 12 times alpha x cubed divided by 12, which is just going to give us 3.05 inches to the 4th. And then a dy squared is just going to be 4.95 times 2.55 squared. This should be around 32.19. And then 17.40 times 0.73 squared gives us 9.27. This becomes 41.46. I don't know why I'm summing the areas. I think there's probably some round off error. Let me double check just to be safe. Just because the workbook here is showing 44.4. So let's see. Yeah, I think I messed it up. I believe this should be 12.62. So I think I made a math error. And then this added to 32.19. Gives us 44.81, give or take. So I think I made a math error initially. No, I think it's just all the round off. And that is going to be in terms of inches to the 4th. Now, with all of that, we can finally calculate the stresses. So because everything is in concrete terms, we could just calculate the stress in the concrete using my over I. The bending moment from the concrete was 40 kip inches. The maximum y coordinate for the concrete from the neutral axis is just conveniently x, which x was 1.45 inches, divided by 44.81 inches to the 4th. And this should give us roughly that 1.306 KSI, give or take. Now for the stress in the steel, we need to transform that material now to steel. So we need to have that term N. We multiply it then by my over I. So it's going to equal 8.06. The bending moment is 40 kip inches. The y coordinate for the steel is just conveniently this dy term, which is 2.55 inches. That's the location of the y bars with respect to the neutral axis, divided by 44.81 inches to the 4th, which will give you roughly that 18.52 KSI that you see on the left-hand side. And that is how you analyze a composite member. You would follow the same exact steps for these materials shown here if you wanted to calculate the stresses. The only difference is that for the concrete, all the tension is carried by the steel, but for this, at least, like, you also wouldn't have to calculate where the neutral axis was in terms of X. You would just be able to calculate the neutral axis since the geometry would already be known. So it wouldn't require you to solve for a quadratic equation. So concrete is kind of unique in that manner. It requires you to do an extra calculation or two here and there. Any questions about composites so far? No? Awesome. All right, moving on is stress concentrations. Basically, we have seen stress concentrations before. It's basically just calculating whatever the average stress is. In this case, would be using the my over I equation. Here they're using C instead of Y. So sigma max, I think I forgot to adjust these slides, but basically your maximum stress would just equal your bending moment multiplied by Y divided by I, and then depending on what your condition is to generate stress concentrations, you would multiply it by K using those tables accordingly. Your textbooks will always have those tables, and on an exam, if I give you guys this question, you guys should be able to, I'll give you guys the tables, but it's basically same exact feature. You would just look at these tables here. You can see that this table would require you to calculate capital D over lowercase d, calculate R over D. You would find out which terms apply, and then just figure out your K value, and then solve for the problem as if you would any other problem, and just multiply your final stress values by K. Make sense? All right. And now the last section, which is the last stretch, which I am now realizing, I don't think I adjusted these slides to basically account for, let me just highlight this all in white, yada, 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 erase all of this. All right, is basically not stress concentrations, but combined axial and flexural overloading. All right, so we've seen previously that the stresses generated from flexure is just basically another type of axial load, right? So when we are dealing with combined flexure and axial loading, they both contribute to the development of axial stresses. So in this case here, you can see that in an example of eccentric loading, we have axial tension from the pulling of the bars. And then because of the moment arm, which is defined by this term D, we actually have normal stresses developed by bending. So what we end up with is this term here, which is basically just going to be our standard internal force divided by the cross-sectional area. And then our equation from bending, which is just going to equal our my over I term. And from here, using linear elasticity and methods of superposition, since we're able to use that because we're making an assumption of the linear elasticity, you should be able to add the two stresses together from any given point and be able to find the maximum and minimum stresses accordingly, which you still end up with a linear distribution. It just now kind of gets shifted as like a y or x intercept due to that axial loading. All right, So another way of just writing this is that sigma x is just going to equal f over a plus or minus my over I. Plus or minus because the bending stresses can be either tensile or compressive, but the axial stress is always going to be either tensile or compressive, not both. And then M is just equal to P times D. Yes?
You said which was either tensile or compressive?
The axial loading. Because for axial loads only, you can't have a member be in tension and compression because it's one internal force. It's like a truss and saying that one member is both in tension and compression for one given load case. It's not true, you know. It's like pulling on a rope and saying that the rope is undergoing both tension and compression. It's either tension or. Only if it was bending would it undergo both. And that would mean that the load is positionally dependent. Make sense? Awesome. All right, so just really quickly, let's go into a quick example with this where basically we have a chain. It's basically subjected to a 160-pound force. And basically assuming that all of the load is just transferred directly through the right-hand side, since you can see it's kind of broken here, so there shouldn't be any load transfer occurring through here. You make an assumption that all of the load is going through here. So with that in mind, I want you guys to actually just take a few minutes, see if you can't take a crack at it yourselves, and just solve for the axial and the total axial stress, the maximum and minimums. I'm also doing that because I need to adjust these slides. We've got it figured out at least. Christian thinks he's got something.
Yeah, let's work on it then.
All right. So, all right. So, hopefully you guys figured out. It's going to be, again, subjected to normal stress and bending stress. So, for the normal stress, treating it as if it's a concentrically loaded member, so basically just back to beginning of the semester, we can calculate the stress due to axial tension as just P over A, which should just be the 160 pounds. That's what this force is. 160 pounds divided by a cross-sectional area, which the area for this is just going to be equal to pi over 4 times 0.5 squared, because it's a chain, so circular, times 0.5 squared should give us an area of around 0.20 inches squared, which when you calculate this, you should roughly get that 815 psi that we had previously computed. Now, the normal stress due to bending, all right, what we need is an internal bending moment. This internal bending moment is just going to be equal to that 160 pounds multiplied by that 0.65 perpendicular distance, which gives us 104 pound inches. So now what we do is calculate sigma x is equal to 104 pound-inches. The perpendicular the location of the extreme fiber, if you guys think about it, since this height has to be 0.5 inches in width, the maximum location from the neutral axis is what? It's half of that, right? So that y just becomes 0.25 inches. And then your I term is just the second moment area of inertia of a circle, which is just going to be pi over 4 times the radius 0.25 inches squared. No, fourth to the fourth. Which when you calculate this, should give you roughly 8,475 PSI. All right, so basically the only thing that's really important here is, let's see, can I ink to shape? Come on. Come on. Draw with touch. No. I don't know how to draw shapes. There we go. Basically, our cross-section, if we just look at our cross-section here, is just, again, dealing with our bending moment and P, and then just analyzing the stresses accordingly. All right, so from here, to determine the maximum and minimum stresses, we just use superposition, and we add the two stresses together, which is how we get the stress distributions that you see there. So 8,475 PSI plus the 815 PSI gives us the 9,290 PSI. And then the 8,475 PSI, which is negative because it's the bending stress, plus the 815 PSI tension stress, will give us the negative 7,660 PSI stress that you see over on the bottom. Now, if we wanted to find the true neutral axis now for this stress distribution, what we need to do is basically just set equal to 0 P over A minus my over I, and then just solve for your y term. So y just gets simplified into P times I over A times the moment, which just simplifies further to sigma times I over M. Now, this sigma x is just the axial stress because that's just the P over A. So that's for axial, which is just equal to the 815 PSI that we had previously computed, times I, which was the pi over 4 times 0.25, times 0.25 inches to the fourth over 4, and then multiply that by the bending moment, which was equal to, where did I calculate it? 104 pound-inches, which means that the neutral axis is actually 0.0240 inches away. So that's this dimension here. Hopefully you guys can see that clearly enough. It's a very small offset. Sure thing. Whoops. And that's it. The only other thing is like another example, but you guys should have access to it, and it's a similar procedure basically. So, yeah, it's 6:15. That's the end of chapter 4. Next week we get into one of my favorite chapters, chapter 5, which is shear and moment diagrams. Yep, homework is due this upcoming Wednesday. If you guys have questions about the project, feel free to talk to me after class or, yeah.
Should we have just like the regular homework due and then the project homework due this Wednesday also?
The only thing I want from the project that honestly probably that's going to be due this Wednesday is just the RFP. Just basically tell me who your teammates are and your proposed methodology for solving the problems.
Okay.
Simple enough.
And all that's on Brightspace? I missed that the first meeting.
I still got to send out like a rubric, but like I mean the RFP is not going to be like anything like graded too severely. It's just me for my own like record keeping purposes, so it doesn't need to be like something super fancy or whatnot. Granted, don't write it on paper. Like type it out, make it look like as if you're submitting to a client. So, but it's not anything that's going to be graded as of right now. It's going to be included at the end of the project as like a very small aspect.
So the RFI is basically the same as what groups we're going to be in?
RFP, yeah.
Or okay.
Request for proposal, yeah. Has anyone even created teams yet? No?